Yes. Now, so what we've done so far, we've talked about sets, writing sets, and subsets is really kind of what we've covered so far. Now, for the most part, all the sets we've talked about are listed or written, have been easily able to write them, put them out. Because 1, 2, 3, we can write either all the numbers or we can write it in a pattern. 2, 4, 6, 8, 10, dot, dot, dot. However, not every set or group of numbers is going to be easily writable, or at least listing all of them. Because if we said that we wanted to write the set of, you don't have to write this down, real numbers.
Good afternoon, Concord High School. If you have not already picked up your JOM school supplies, pick up them. Please pick them up from Brooke in the Federal Programs Office at the Community Center. Thank you.
So if we wanted to write this set, so the set of real numbers greater than 0, as we've done it up to this point, well, we would start with 0, yes? What would our next number be? Right, because we could have 1. Here we have 0.1. We could also have 0.172638497, because that's technically bigger than 0. I could also have 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8. Those would all be greater than 0, yes? How about 2/3? We're going to list 2/4 even though it is 1/2, but we'd also have 2/5, 2/6, which is 1/3, 2/7, 2/8. But we could also have 3/4, 3/5, 3/6, 3/7. I'm going to stop there, but is it feasible for us to actually write or list out all the real numbers greater than 0? No. These are some that we start getting to the point where we are going to have to know the number sets, list the type of numbers, and start actually writing inequalities, intervals to actually describe it, because actually writing all the real numbers greater than 0 is not doable. It's just not. So we actually need intervals, and we're also going to be using something called set builder notation. Now with intervals, we have 2 types, bounded and unbounded. In geometry, we normally call unbounded, or kind of that form, a ray. Bounded intervals have 2 endpoints, and it's all the points in the middle. An unbounded interval has 1 endpoint and continues indefinitely in one direction. That, by definition, is a ray. I will tell you this as a side note. I did have a friend named Ray in college. I made lots of Ray jokes. He got very tired of them very quickly. If you did not know, light rays, as they approach strong gravitational pulls like the sun or earth, will bend. I was like, hey, Ray, how's it going? You're looking a little bent, because he's close to the earth. He did not find that funny. He found it funny for about a bit, and then didn't. Or they, at John Brown University, the all-guys dorm, at least when I was there, would put up a Christmas tree every year. It is pretty big. The dormitory has an interior atrium. It has 3 floors. That tree hit the ceiling every year. So it is a 3-story, it's 36-foot tree, Christmas tree every year. He was helping with putting it up, so they would have, from the 3rd floor, they would tie ropes to the tree to help pull it so that they can build the base. He was up there pulling the rope, and I saw him up there, and I yelled, hey, Ray, don't go too far. You can only go in one direction. He would give me about a chuckle and then get very frustrated. because I would come up with these all the time. But unbounded, one endpoint continues in one direction. Bounded, we have two endpoints. Now at the bottom of that page, bounded intervals, we have all these words. Let A and B be two real numbers such that A is less than B. Then A and B are the endpoints of four different bounded intervals on the real number line. That is a whole bunch of words. That first sentence, let A and B be two real numbers such that A is less than B. We say this for one main purpose. We want to describe any and all possible bounded intervals. So A and B are just a number. They're any number. But we're saying whatever A is, B has got to be bigger than it. So if A is negative 200, B can be anything bigger than 200, negative 200. That's all it's saying. So for any two numbers, any two spots, one of them smaller than the other. That's all we're saying in the first sentence. Second sentence, then A and B are the endpoints of a bounded interval. They're the two endpoints. And we have four ways that we can set this up in general. The first one, A is less than or equal to X is less than or equal to B. Essentially, in interval notation, we're saying that both endpoints are included, brackets. So that's all that's saying there. Or, we don't have to include either endpoint. A is less than X is less than B. They're both open. So given two endpoints, they're either both going to be included, both not going to be included, or the other two cases is that one is included and one's not. A is less than or equal to X is less than B. Or A is less than X is less than or equal to B. And this is nice, and I like this in mathematics that we can do this. Because instead of having to list out every possible case, every possible scenario, which is not possible because there's too many numbers to list out, I can generalize every bounded interval by these four statements, no matter what the numbers are. As long as A is less than B, any set of numbers for A and B will follow one of these four. And the nice thing to know, especially with bounded intervals, we have two endpoints, no matter if we're going to interval notation or inequalities. We know we have two endpoints. We know it's bounded. It's got to fit one of these four. So especially if inequality is something you struggle with, having this there, looking back on it, is going to be helpful, because if we figure out what A and B are, we fill in the blank. Questions on bounded intervals? Now the other type we have is unbounded intervals. Let A be a real number. Let A be any real number. Each interval on the real number line shown below is called unbounded. So we have one endpoint and it continues indefinitely in one direction or the other. So as we see with the first one, we're saying that X is greater than or equal to A. All the numbers bigger than or equal to A. As an interval, we have a bracket with A, and it's going to go to infinity. Since we don't have an endpoint, it's just going to infinity. Exactly. If you struggle with writing infinities, do you all know the trick for it? Turn the paper sideways and write an 8. It's going to go that direction. Now, infinity and negative infinity will always have a parenthesis. We will never be able to get to infinity no matter how hard we try. I will drive that point home here in a little bit. Now, we also have the case where X is just greater than A, so we have a parenthesis, A comma infinity. We also have the two cases where X is less than or equal to A, or X is less than A. And this chart is really nice because depending on the setup, they tell us, okay, we know we have one endpoint, it's going to negative infinity, it's going to positive infinity. We can just fill that in for A, because that would be our one endpoint. We get in the other information. Now, I do like to include the last one, negative infinity to infinity. It's all real numbers. It just satisfies the entire, or covers up the entire number line. Questions on any of this here? We good with everything so far? Yes. Now, up to this point, especially every time you cover inequalities or especially interval notation, we just say parentheses around infinity because we can't get there. It's really big. Yes? So I'm going to actually drive kind of that point home why we say that or why we do that. One of them is infinity is not a number. Infinity is not an actual number. Like 1, 2, 3, we don't have a definite value. It is more of a thought. We understand what it is. It's just something that's massively big. That's all infinity is. It's not an actual number per se. But also, some infinities are bigger than others depending on the context in which we use it. Because if we're talking about just in number sets or types, in certain categories, yes. In certain situations, no. It's one of those kind of tricky things. A thought experiment that they've come up with to kind of help visualize the fact that we can never get to infinity is something called the infinite hotel. So we're going to have this infinite hotel that has an infinite number of rooms. For case in point, I'm going to be the desk clerk at the infinite hotel. Now, on this night, the infinite hotel with infinite rooms is booked. There is no open rooms in the entire hotel. Even though we have infinite number of rooms, every single one of them is booked out completely. However, as I'm manning the desk, someone comes in and asks, hey, can I get a room? Being a good clerk as I am, I want to try to get him a room. So after thinking for a while, I come up with a decision. The idea is I'm going to tell the person in room 1, hey, move to room 2. And politely ask the person in room 2 to move to room 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7. We're moving everybody down one room. There's an infinite number of rooms. So they're all able to move down one room, which means room number 1 is now empty. So the new guest is able to move into room 1. Even though in this hotel, all the rooms were booked, we were able to still get one more person in. We can't get there. We can't actually get to infinity. That's why it's not a bracket. We cannot actually reach that point. Well, apparently the hotel was doing super well. And right next door, I don't know why they built it right next door, but they built a second infinite hotel next door. They renamed the first one Infinite Hotel A and the second one Infinite Hotel B. In a tragic accident, Infinite Hotel B burned to the ground. Luckily for us, every person that was staying in Infinite Hotel B, all infinite number of them, because it was booked out too, made it out alive. They're all safe. But all of them need a place to stay tonight. And after thinking for a while as the desk, I'm like, I got it. What I'm going to do is I'm going to ask the person in room 1 to move to room 2. Well, you're like, that's not any different. However, I'm going to ask the person in room 2 to move to room 4. We're going to ask the person in room 3 to move to room 6. The person in room 4 to move to room 8. The person in room 5 to move to room 10. The person in room 6 to move to room 12. We're asking them to move to the next even number. Well, how many positive even numbers do we have? Infinite number of them, yes? But that means what? Rooms 1, 3, 5, 7. All the odd numbered rooms are empty, yes? Well, there's also an infinite number of odd rooms. So now we can move all the infinite people from Hotel B into Hotel A. We just smashed 2 together. We're starting to see why we can never actually get to infinity. And it's one of those concepts that is very complex, but also something like this here makes it very understandable all at the same time. The fact that if last week you'd have been able to tell yourself you're going to be able to understand how to actually fit 2 infinities into 1. Probably thought that crazy, but here we are. So all that's to say is that's why we, especially with unbounded, we've got that parenthesis with infinity. We just can't get there. It's more of a concept than it is an actual number. Now, all that to say is we're going to actually write inequalities as intervals. We'll get to the point where we're writing intervals as inequalities. We're going back and forth. Now, for some, being able to see it graphically helps. For some, I would say just looking at our chart also helps. So if we wanted to graph this, we see here -2 is less than or equal to x is less than or equal to 3. How many endpoints do we have? 2. We got the 2 endpoints, yes? So that means it's bounded. So if we were to graph it, we would also have 2 endpoints at -2 and 3. Is -2 included? Yes, because it has that equal sign underneath it. It is included. So if we were graphing it, we would fill it in. Is 3 included? No. And because x is in the middle, we shade in the middle. So this here is the graphical representation of the inequality. -2 is less than or equal to x is less than or equal to 3, yes? Is that what it asks us to do? No. It asks us to write it as an interval. So if graphing it helps you see and get to the interval, graph it. If you don't need it, don't graph it. Because unless it's specifically asking for the graph. It helps us kind of see from here and here that we had 2 definite endpoints. -2 and 3. Yes? Is -2 included? So it would be a bracket. Is 3 included? So it would be a bracket also. Bracket -2, comma 3 bracket. Questions on this here? Now, I said a bit ago we could use our bounded interval chart because we have this here, yes? I'm going to write it up here. -2 is less than or equal to x. Which one of these 4 does it match up with? Well, it matches up with the top one, yes? What is A in our example? -2, what's B? 3, because A, -2 took the place of A. B was replaced by 3, yes? Which means here, this A has to be what? And this B has to be? That's it. Match it up, replace it. There's another way we can do this. X is greater than -1. I'm going to go on and graph it. Now, if you notice on the graph of the last one and this one, I'm not putting 0, I'm not scaling, I'm just putting the key information. I believe there is going to be at least a few problems that ask you to graph it. This is all I'm looking for. I'm not having you give me the whole scale, everything. The main thing is the numbers are placed in the position they should be placed. Negatives to the left, positives to the right. Smaller to the left, bigger to the right. if we're graphing this, is -1 included? If it is, do we have an equal sign with our inequality? We don't have the line under that greater than, so it is not included, because if it's greater than or equal to, less than or equal to, we include it. Because it is not, we leave it open. Now, do we shade to the left or to the right? So what's a number that would be to the right of -1? 1. What would be a number to the left? -2. So if I said replace x with -2, is -2 greater than -1? No, this is not true. This is a false statement, yes? Because any place that we shade should be a true statement, should make the statement true, yes? Any part of the equation or the line that is not included should not be shaded. So because -2 does not give us a true statement, it should not be included, it should not be shaded. So we're not shading this direction, we have to shade to the right. Now, if we want to make sure, a number that we just picked to the right of -1 was 1. Is 1 greater than -1? Yes, it should be in the shaded region, so we shade that direction. We've seen that before, hopefully. That makes stuff, especially checking shading, a lot easier, a lot nicer. That works on the ACT too. Given the following inequality, which of the following is the correct graph of the given equation? Even if it's a system, we have more than one inequality. The point in the shaded region should be true for all statements. So you can pick one of the answer choices, the graphs of it, and fill it in for that equation. If both of them are true, it should be included. If they're not, that answer choice is out. It goes the other way too. Given the following graph, system, whatever it is, which of the following is the correct equation for the given graph? Pick a point in the shaded region and plug them in. It should make one of them or both of those equations true. Are we good with this so far? Yes? All right, now we need to actually write the interval. The one endpoint we have is -1, yes? Now we need to figure out, are we going to infinity or negative infinity? Infinity is always bigger, negative infinity would be smaller, yes? Which direction are we going? Positive infinity. Bigger numbers on the right, smaller numbers on the left. Bigger number, infinity, can be bigger. So put it on the right, and infinity and negative infinity will always have a parentheses. -1, is it included? Did we shade it in? No, so it's going to be a parenthesis. Or unbounded interval, we only have 1 point, yes? And we said x was greater than -1. Well, what's a? So that means this a here has to be also works. Questions on A or B? Let's look at C and D. C, they didn't give us an interval or an inequality, but we still need to write the interval. Is this bounded or unbounded? Do we have 2 endpoints or 1 endpoint? 2, so it's going to be bounded, yes? And we know those 2 endpoints are -3 and +4. If looking at the charts helps, well, we know 1 is bounded, or 1 is included, 1's not. So we're not looking at the top 2, we're looking at the bottom 2, yes? Would it be the third one or the fourth one? That's going to be that third one. The left point is included, the right one's not. Because it was -3 and 4. So A is taking the place of -3. 4 is taking the place of B. So that means here we would have -3, 4. And if you're wondering, yes, you can write that whole chart on the review sheet if you want and use it on the test. D, bounded or unbounded? Unbounded, we only have one endpoint, yes? Is that endpoint included? Yep. So we're really looking at this one here. And what's our value of A? Because this here is 3, yes? So that means as an interval, we would have parentheses -infinity, comma, 3. Because it's included, we have a bracket. That means also if they give us an interval or inequality, we can use that chart and get the other one. Figure out what A and B is, replace it. Questions on any of this here? Now, as we discussed already, we kind of talked about it closer to the start. I've kind of noted or mentioned the fact that not every interval or every set of numbers is easily writable. We can't just list out all the real numbers greater than 0. We really can't even write out all the real numbers greater than 0 and less than or equal to 1 or less than 1. There's too many. So we need a way to write it. And that is set builder notation, where you're going to use symbols to define a set in terms of the properties of the members of the set, of what it makes up. Now, for the longest time, I actually had something in this other than a triangle and a circle, but I feel like and felt like this is going to be easier for us to grasp than having something we're more used to seeing. Now, in the triangle spot, what goes in this place is a description, or we write and describe what is our group. What kind of numbers are we talking about? What is our group? What are our number set? Are we talking about real numbers, rational, irrational, whole numbers, natural numbers? What is our number group? That's what goes there. The circle is our description. What type of numbers, like what is actually describing the group of numbers? Is it greater than 1? Is it less than 0? What is, and most of them are going to be inequalities. We can have some equations and specific information, but that's going to be inequalities. We cannot have an interval in set builder. So questions on what the triangle or circle is. Now we have the bar in the middle, yes? It means such that. Given this type of given this number set, such that this describes it. For all real numbers x, such that x is greater than 1 would be set builder. What does that look like? Well, it looks like these here. Because the first part tells us the type of numbers that we have, such that it follows this description. So our first one here, brace x bar, if we read it, is the set of all real numbers x, such that x is greater than a, or x is less than a. Number set, description. So if I wanted to look at a graph of this here, we'd have some point on there that is A. A can be any number. We're just saying whatever x, the values of x is, have to be less than it. So graphically, this is what we're talking about. So if A was 4, we're talking about the set of all real numbers x such that x is less than 4. So we're now able to write in symbols using notation to actually describe the set of all real numbers greater than or equal to 0 without having to list them all. The second one I find it kind of interesting because if we read this here, brace x bar, the set of all real numbers x such that x is not equal to 3. So we're saying that x cannot be what? 3. So what could x be? Anything. It can be anything but 3. So if I were to graph this, we would put a spot at 3. But we wouldn't fill it in because x cannot be 3. But where would we shade? We would shade to the right of it because it could be any number bigger than 3, yes. But it could also be any number smaller than 3. It's everything but 3. That's kind of an interesting graph. It's pretty much everything, but it cannot be 3. Don't know what 3 did, but it's not included anymore. We good with the first two? The third one, brace x bar, the set of all real numbers x, such that -4 is less than x is less than or equal to 6. If we're graphing this, really, it's like, okay, cool. We're talking about all real numbers. Our two endpoints are -4 and 6. And we are going to have everything in between, yes? Is -4 included? No, so it's going to stay open. Is 6 included? So we fill it in. Questions on the first three? Now, the last two, graphing them, isn't convenient or nice, because we'll look at the last one first. The set of all real numbers x such that x is even. Trying to actually graph out where all the even numbers are. Not as doable, but this is what it's saying. The set of all real numbers x such that x is even. I include this in here to show you it doesn't just have to be inequalities. We just can't use intervals. We can actually give a description in words. X is even. Kind of make sense? Because there are ways to actually write it mathematically, but I don't think you'd want to see it. It is more complex than it's needed. The one above it, XE space bar. This is element. X is an element of y'all remember what that symbol is? Take a look, because we had it yesterday. Should be on page 1. Integers. So x is an element of the integers such that. So what I've done is I've changed the number group that we're talking about. So I'm not talking about all the real numbers. We're just talking about the integers, our positive, negative counting numbers, such that x is greater than or equal to -9. We're not talking about all of our decimal, our rational, our irrational. We're just talking about the integers. It gives us a way to actually describe this set and give it more information. Is this the only way to write it? No. The way that the textbook does it is we do the set of all real numbers x such that x is an integer and x is greater than or equal to -9. That is saying the exact same thing. For all real numbers x, so for any number x, such that x is an integer, so we've removed rational, irrational, all those numbers out, and it has to be greater than or equal to -9. However, brace x element of the integers, x is an element of the integer such that x is greater than or equal to -9 is the exact same thing. I like the top one better. That is a lot less writing. It is simplified, condensed. And well, yes, if we wanted to, we could actually write it in another way. This way you're not going to actually do. For all real x in the integers such that x is greater than or equal to -9. If you ever get to the point, upper level math, and start writing proofs, these are the statements we are actually looking at. These are proof statements. I will tell you this now, this is above and beyond. They get very complicated very fast. For all real m and n in the real numbers, there exists a p in the real numbers such that m times p is equal to n, or n times p is equal to m, such that m is equal to n and p is equal to 1. You don't ever have to know that. You don't even need to write that down. I wouldn't write that down. This here, if I remembered it right, is the statement or statement we can use for a proof for prime numbers. Because if I were given two numbers, m and n, the only way I can multiply another number with m to get n, and, that's probably supposed to be an n with that same number p, to get m, the only way I can do this operation is one of two things. Either m and n are the same number, and p is 1. I'm only multiplying by 1. But again, don't have to do that. Don't ever have to focus on that. But again, it's starting to give us ways to actually start describing lots and lots of things with not a whole lot of information. And we know what we're talking about or know what others are talking about. Let's look at these here. So they want us to take this set builder notation and graph it. A, for all x, so for all x is, well, for all values of x in the real numbers, x is a real number such that 2 is less than x is less than or equal to 5. Really, we're saying for any real number x, 2 is less than x is less than or equal to 5, yes? For us, we're really just focused on this. So where are our endpoints? Is one or both or neither included? Which one? 5 is included, so we would put in. Because x in the middle, we shade in the middle. And when you shade, if you want to do that squiggle line, do that squiggle line. I find it easier to actually be able to read the line than just shading over the top of the line. Because unless you shade really, really dark, it's hard to see. That's all I need. Questions on A? B, we have a compound inequality. For all real numbers x, such that x is less than or equal to 0 or x is greater than 4. We have two unbounded intervals. Yes? X is less than or equal to 0. So let's focus on it first. So at 0, I would have a circle, yes? Would it be filled in or open? Filled in because we have that equal sign. Now, would we shade to the left or to the right? Left. All right. X is greater than 4. Where's our endpoint? 4. Opened or closed? Open. Shaded to the left or right? Yep. Now, most of the time with these or statements we're very much used to, we get the two endpoints and shade in opposite directions, yes? Is it possible for them to be going in the same direction, or actually going towards each other instead of away? Well, yeah. They can actually go towards each other. If they do, we fill up the whole thing. That's our negative infinity to infinity. If or statements actually go towards each other, we fill up the whole line. That is infinity to negative, or negative infinity to infinity. All right. Let's look at this one here. The set of all real numbers x such that x is less than negative 2 or x is greater than 0. X is less than negative 2. Where's our endpoint? Negative 2. Open or closed? Open. Shaded to the left or to the right? Left. X is greater than 0. Endpoint is at 0. And then we obviously shade to the right. Or hopefully obvious. If not, we can always get our test points and see which way we go, which one makes the statement true. That's it. Questions on this here? Yep. We'll do these last two, and we'll finish the note sheet tomorrow. Now, this will be more kind of closer to the homework assignment, probably what you're going to turn in. For all real numbers x such that negative 6 is less than x is less than or equal to negative 2. I'm not saying closer to what you turn in the fact that they're going to be different than the last few. You're just not provided a number line. Now, for this one here, we do have two endpoints, yes? So on the homework, I'd make 2 points or 2 marks on my number line. So I draw a number line, make 2 spots. Negative 6 is the smaller one, negative 2 is the bigger one. At negative 6 and 2, we're going to have circles. Negative 6, is it opened or closed? Open, not equal to it. Negative 2, is it opened or closed? Closed. X is in the middle. So we shade in the middle. That's it. And especially on the homework, you don't have to give me a 0. You don't have to give me that reference point. This is all I'm looking for. The only thing that I will, not so much not accept on the homework, I will mark it off. If you do it on the test, I will take points. Do this here. Smaller numbers on the left, bigger numbers on the right. We actually need the graph set up properly. So we need negative 6 on the left, negative 2 on the right. That's all we need. Most of the time when we do include or have y'all include the 0, it's just making sure y'all don't put it in the wrong order. We will finish this tomorrow.